Another example from acceleration problems. This is, I would say, it's a complete example, and it deserves to spend like, I would say, if you want to solve this problem from the beginning to the end of it, and this is your first time doing similar problems, you should spend at least 30 minutes thinking about it, trying to solve this. Okay. Problem 108, chapter 5. So read the problem carefully. We have this slider which is moving down with the velocity of 2 feet per second, but acceleration of it is upward. It is 1.2 feet per second squared. We had exactly the same problem before. We analyzed the velocity of it and we found the angular velocity of AC, if you remember that. So if you want to solve this problem from the beginning, you must actually find angular velocity of this too. Before that, what is the question? The question is, what is the acceleration of point A? In the previous part, we found the velocity of point A. Now, we have some information about the acceleration of this rod, 1.2 feet per second upward, and we are trying to find acceleration of point A. Okay? Try your best to solve this problem, at least spend 30 minutes on this, then watch the rest of the video. Okay, like many other problems that we did before, to analyze acceleration of a mechanism, you must do velocity analysis before. For example, to solve this problem, we need to know what is the angular velocity of this rod, okay? So let's say we did that part, which we did that actually in a few videos before. Angular velocity of AC, we found it to be 10.93 radian per second in counterclockwise direction. Okay. I'm gonna assume you did that part and you know how to find this angular velocity. So after finding this, to find acceleration of A, what we need to do here. First, look at the problem and see what information we have about this mechanism. So about point B, we know the velocity of it and also the acceleration of it. It is given, right? To find the velocity, to find the acceleration of A, so naturally you may think about writing the relative acceleration equation between A and B. But if you write down that equation, you are going to have three unknowns in that equation. Because acceleration of A is unknown, which means two unknowns, because it's a vector, we don't know the direction of this acceleration, we don't know the magnitude of it, so we have two unknowns here. And also alpha of this bar is going to show up in that equation too, so three unknowns. The relative acceleration equation is a vector equation. In 2D, it means it is two equations, right? But we have three unknowns here. Two components of acceleration of A and alpha of the bar. So we are not going to be able to find acceleration of A using only that equation. We need to find alpha of this bar, the angular acceleration of ABC. How we can do that? We need to see what else do we know about this mechanism. So look at point C. Point C, we know the velocity and acceleration of this point must be along this incline, right? So we have a piece of information here and we need to use it to find, for example, the alpha of this bar. Now, if we write the acceleration equation between B and C, then acceleration of C is going to be unknown, but it is one unknown. We know the direction of it. And alpha of this bar is another unknown in that equation. So we are going to have two unknowns and it is two equations, so we should be able to find acceleration of C and also alpha of BC, ABC, which we were looking for, right? So the good idea is starting from that. So the relationship between acceleration of A and C, or the relative acceleration equation between B and C, is this. Acceleration of C is equal to acceleration of B plus alpha cross product to BC, then omega cross BC, or negative omega of this bar, which we called it AC squared, times BC. So let me show that here too. This is omega of BC, and also I'm assuming alpha of BC is in the same direction too. Let's call this, sorry, I called this BC, but here I called it AC. Let's make all of them BC. It doesn't really matter. So this is the relationship between acceleration of B and C, right? Now let's fill in all of these vectors. Let's write them down. Acceleration of C, we don't know the magnitude of it, but we know it's going to be, this is the direction of it, right? So I'm going to assume acceleration of C is upward. It doesn't matter if you assume it is downward. At the end, it's going to be positive or negative. And I'm going to use this system of coordinate, x and y, and write all the vectors in this system of coordinate. Acceleration of C as a vector is AC times this direction, right? So AC times the unit vector in this direction, which is gonna be cosine of 50i and sine of 50j, plus sine of 15. So this is acceleration of point C, which AC is unknown. The magnitude of this acceleration is equal to acceleration of B. We have it. It is given 1.2 feet per second squared, and it is upward. So it's going to be positive 1.2. Alpha of BC, the magnitude is unknown, but we assume it is in the K direction. Then cross product to BC. And BC is 3 inches in this direction. So it's going to be 3 times the unit vector in this direction. And if I want to make it fit, I need to divide it by 12. So 3 divided by 12 foot times the unit vector in this direction, and this angle is 30 degrees. So the unit vector in this direction is going to be cosine of 30 in the I direction minus sine of 30 in the J direction. Okay. Negative omega BC squared times BC. So negative 10.93 squared times BC. Again, the same vector, 3 by 12 times cosine of 30 I hat minus sine of 30 j hat. We have a cross product here, so you need to cross product k to I and also k to j, and do this cross product. After doing that, we can separate I and j terms and find alpha and also acceleration of C. I'm gonna let you do that yourself. So separating I and j terms, 2 equations, 2 unknowns. Unknowns are AC and alpha. Just to save the time, alpha of this link BC is gonna be negative 126 radian per second square. And also AC, which we don't need it, but we can find it from this equation. AC will be negative 43.1 foot per second square. Okay. After finding alpha of this link, now I'm going to be able to find acceleration of A by writing the relative acceleration equation between A and B. So let's do that. Acceleration of A is equal to acceleration of B plus alpha of this link, which we called it A alpha BC, cross product to BA, negative omega of this link, which we called it omega BC squared times BA. Now look at this equation. We know this acceleration. We found alpha in the previous step. BA is this vector. You can simply write that vector down in terms of I and j. And same thing here. Omega BC, we found it in the previous part, right? From actually previous problem. So because we have everything, we just plug them in, then you're going to be able to find acceleration of A. So again, just to save time, I'll let you do that part. If you plug in all the numbers, acceleration of A is going to be 41.6 in the I direction plus 13.55 J, and the unit is foot per second square. And the magnitude of the acceleration, of course, is going to be 41.6 squared plus 31.55 squared root square, right? So the magnitude of the acceleration, 41.6 squared plus 13.55 squared, which is going to be 43.8 foot per second squared.